Dependency injection, often abbreviated as simply DI, is a design pattern that supports the development of loosely coupled code. The use of dependency injection supports implementation of two related concepts: inversion of control and the dependency inversion principle. Dependency injection is a foundational concept in ASP.NET Core, upon which the rest of the framework relies heavily. It is strongly encouraged that developers take advantage of dependency injection when building ASP.NET Core applications. In fact, you must work quite hard against the framework to avoid using it. We'll begin by identifying some architectural problems inside the tennis booking application. This page is the homepage for the fictional tennis club. At the top of the homepage, the owners have a requirement to display the current weather conditions near the club. Since I'm based in the UK, perhaps I could have just hard-coded this as a rainy forecast. Here is the ASP.NET Core Razor page model, which handles requests for the homepage. It has an onGet method, which populates the model used to build and return the homepage content. This method currently uses a class called Random Weather Forecaster to get the current weather conditions. To produce the page model, the onGet method calls a method on this class. This is known as a dependency because the onGet method and the index model class is now dependent on the Random Weather Forecaster to complete its job. Currently, the index method is responsible for the creation of the Random Weather Forecaster instance on which it depends. It does this using the new keyword. Whilst everything works as expected, there are a few problems with this current approach. Because it's responsible for creating an instance of the Random Weather Forecaster, the onGet method is now tightly coupled to the current Random Weather Forecaster implementation. Tight coupling is considered an anti-pattern in software development because it makes it harder to maintain code. Well-factored code will include dependencies between classes, but we want to avoid directly coupling those classes together. To illustrate why this current design can be problematic, imagine a requirement to add an improved weather forecasting implementation to the application. We can expand the tennisbookings.shared class library project and right-click to add a new class. Let's call it Amazing Weather Forecaster. We'll include a getCurrentWeatherAsync method on this class, which accepts a city and returns a weather result. For reasons that will become apparent later, I'm making this method asynchronous, which means the result is wrapped in a task. We'll have this implementation always return a fixed result, where it's sunny every day. That would be pretty amazing. If we want the onGet method to use this implementation, then we must update its code to create an instance of the Amazing Weather Forecaster instead of the original Random Weather Forecaster. Now, this makes the application harder to maintain because changes downstream can ripple through layers in the codebase. A second problem arises when we want to unit test the onGet method. The onGet method has logic for adding a weather description to the view model for the page, and this is based on the weather result from the weather forecaster. Now, it would be reasonable that we want to test that the expected weather description is set on the model for each of the possible weather results. Inside the test project, there are two unit tests that begin to cover this scenario. I'll right-click inside the class and choose Run Tests from the menu. Oh no, one unit test has failed. The test expects to cover the case where the rain condition is returned. Because the onGet method is responsible for creating the weather forecaster dependency directly, when under test we can't control the implementation that's used, nor the result that the getCurrentWeatherAsync method returns. The Amazing Weather Forecaster implementation returns a sunny weather condition every time it's invoked. So at this point, reliably testing the logic of our index model is pretty tricky. We'll resolve this later in the module once we've refactored the application. Before we continue, let's switch the onGet method back over to using the Random Weather Forecaster for the time being. So what can we do to address these problems? A good option is to clean this code up, invert the control of instantiation of the random weather forecaster instance, and take advantage of dependency injection. The dependency inversion principle recommends that our classes rely on abstractions rather than implementations. Currently, the index model is tightly coupled to the random weather forecaster implementation. We'll refactor this application by creating an abstraction to reduce the coupling between classes and their dependencies. We'll achieve this by extracting a simple interface. We can use the built-in Visual Studio refactoring tools to do this, but you can also modify the code by hand if your editor does not support refactoring in this way. I'll right-click on the class name for the random weather forecaster and choose the Quick Actions and Refactorings menu item. I'll choose Extract Interface from this menu, and in the dialog, I'll name the type iWeatherForecaster. We'll allow the tooling to include the getCurrentWeatherAsync method as a member of the new interface and accept all of the other defaults by clicking OK. A new iWeatherForecaster interface is now defined within the application. The tooling has updated the Random Weather Forecaster class to declare that it implements this new interface. This is our first improvement. This will help keep the code more loosely coupled as we move forward. As with any abstraction, we can declare multiple implementations for it. Let's update the Amazing Weather Forecaster class here to identify that it also implements this new interface. Because I was careful when I created this type, its signature already matches the interface, so no further changes are needed here. With the interface abstraction created, it's time to move on to applying constructor injection. Constructor injection provides a way for dependencies to be passed into the class via its constructor, rather than the class creating instances of those dependencies itself. This example class depends on the SomeService type to perform its work. It's currently tightly coupled to that specific type and controls the creation of an instance. Constructor injection can be achieved by making dependencies parameters of the constructor. Instances of those parameters must be supplied by the code creating an instance of the example type. We can store those injected dependencies into private fields so that they're accessible from methods of the example class. The consuming code no longer creates its own instance of SomeService. Instead, it uses the instance passed into and assigned by the constructor. This sets us up to implement a form of the inversion of control design principle, also abbreviated as IOC. IOC can take a few forms. In this scenario, we're inverting control of the creation of dependencies, allowing a component other than the example class to take responsibility for creating and passing in those dependencies. This, combined with depending on the interface abstraction, helps us start to achieve loose coupling in the code. To implement this in the tennis booking application, let's refactor the page model by implementing constructor injection. We'll create a constructor accepting an iWeatherForecaster parameter. We can then use the Visual Studio tooling to help us create the field. I'll press Ctrl+, which brings up a menu containing some refactoring options. The second option is the one we want, which will create and assign a field. The preview demonstrates the change that Visual Studio is about to make for us once we press Enter. A field is created and assigned from inside the constructor. Using the read-only keyword here on the field is a good practice, as it prevents methods from accidentally assigning a different value for this dependency after the index model is instantiated. The code now supports the dependency injection pattern, because we allow the injection of any dependencies required by this type at the point it's created. We need to update the onGet method to use the iWeatherForecaster provided via the constructor. We no longer need this line, which creates an instance of Random Weather Forecaster. Instead, the code can access the iWeatherForecaster instance stored on the private field and invoke the getCurrentWeatherAsync method that's defined on the interface. At this point, I'm going to run the application, but I'm expecting it to fail, as you'll soon see. As expected, an invalid operation exception has been thrown within the ASP.NET Core framework. The error message gives us a hint as to the cause of the problem. While attempting to activate the index model, a service for the iWeatherForecaster type could not be resolved. We've got this exception because we haven't configured the application so that the framework knows how to resolve this runtime dependency. This is a runtime exception and not something that causes a warning or an error at compile time. This is a common oversight, so don't feel bad if you see this occasionally when you're developing your applications. We need to complete the inversion of control here so that the framework can take responsibility for creating and injecting the required dependency.